Okay, welcome to part one of our little lesson on Extrema, where we're going to find out how to find maximum values and minimum values of functions. So it's really the first significant application to functions that we can use with our calculus other than just finding slopes and tangent lines and things like that. So the idea is we want to understand what we mean by extrema, and of course it's kind of just how it sounds. The extremes are going to be the highs and the lows of a graph, and we have a formal definition of what it takes to be a minimum and a maximum here, and basically what we're saying is you're going to have a minimum value if it's less than or equal to all the other values on an interval, and you have a maximum if it's, that's a little typo there, that should be a greater than or equal to right here. It should be greater than or equal to all the other y values on an interval. So you get some wacky situations where you could have a graph that literally has a horizontal line or something like that. And that spot right there is technically both a relative minimum and a maximum according to these definitions, because it's greater than or equal to all the other y values in the area. But I'd say if you want to think about what we're talking about with minimums and maximums, you can look at this picture here, get a sense of the fact that we've got a minimum down here at the bottom, the low part of that valley, and similarly we have a max up here because on this little interval from A to B that appears to be the highest value. Now this spot right here would also be considered a relative maximum because it is in its little neighborhood the highest y value. So what we're going to focus on first are these relative mins and maxes, these places like this one and this one, where you're either at the top of a mountain or the bottom of a valley. In the next lesson, we'll talk a little bit more about absolute maxes and mins. That's where we're finding the ultimate highest y value of a function on an interval, or the ultimate lowest value of a function on an interval. That gets just a tiny bit more complicated. But for this, finding these relative mins and maxes, what we're going to do is take a look at where these things occur, which is places where the graph has like a zero slope tangent, either like that or maybe like this. You might have a minimum value down here or a maximum value up there. Similarly, you can have relative mins and maxes that occur at places where maybe the curve comes to a sharp corner like that, or maybe it comes down like this. So these two examples here are examples where the slope would be undefined at those points, and they can yield mins and maxes sometimes. And these are examples where the slope is zero. So we're going to identify critical numbers as places where the slope is either zero or undefined. So you can look at that. Critical numbers are x values where the derivative is either equal to zero or the slope is undefined. They're going to be the gateways to finding our mins and maxes. So we better get good at finding those. So that's what we're going to do. We have this first example down here. The function is x to the fourth minus 4x squared. I think I'll write that up here. F of x is x to the fourth minus 4x squared. And so we need to find the places where this function has a derivative that's either zero or undefined. So we take the derivative, and simple enough, just straight up power rule, 4x cubed minus 8x. And you'll see me do this a lot from this point on, where we want to find out where this function is equal to zero. So I'm going to use a triple equal sign here, and that shows the reader that we're setting this function equal to zero. It's not inherently equal to zero, and we'll solve that. We would also be curious about where functions are undefined, but this, of course, is a polynomial function, and polynomial functions aren't undefined anywhere. The only time you'll have to worry about functions being undefined is if it was a rational function, something like that has a denominator. So maybe you had a derivative, just write one down here, that was something like 2x plus 3 over x plus 1. Well, we would have to recognize that x equals negative 1 is a value that would make the denominator 0, which means the derivative would be undefined, which would mean that would be a critical number. I'm going to use CN as my abbreviation for critical numbers. Similarly, we'd looking at the function and we'd say, hey, the numerator could be 0 if x was negative 3/2, and that would also be a critical number. So these two numbers would be places that could potentially be maxes or mins for that function. Anyway, back to our story. We have a much simpler case here. The way to find out when a polynomial is equal to 0 is factor it. And of course, the first rule of factoring is your GCF. So I'm going to take a 4x out and be left with x squared minus 2. And now we realize that we have two things, well, maybe three things that we have to focus on. We could think about 4x equaling 0. Of course, that means x equals 0. Or x squared minus 2 would equal 0, which means x squared equals 2, which means x equals plus or minus the square root of 2. So those are our critical numbers. So if we wanted to make a little list of our critical numbers, we'd say x equals 0 and x equals plus or minus root 2. And so that's what the question was asking. And so in order to determine whether those things were mins or maxes, we would have to just take another little step in the process. And because that's what we're focusing on, I'm going to extend this problem a little bit and say, let's find out if these guys have mins or maxes at any of these places. So here's what we're going to do. We're going to set up something called a sign chart. And you may have seen this in Algebra 2 when you were studying rational functions that look like this. And what I'm going to do is just list my critical numbers in ascending order. So negative root 2 is the smallest one, then 0, and then root 2. And what I want to do is track the signs, the positiveness or negativeness of my derivative by tracking what's happening with this at these critical values. So I know that the value of my derivative is 0 at these three places. So I'm going to put little zeros there. And what I'm going to do is think about having these two factors right up here, the 4x and the x squared minus 2. And to show that, I'm going to put little sets of parentheses like that and that. So it's as if I have two sets of parentheses because I've got two factors there. And I'm going to do that in each little interval. Now, what I'm going to do is test a value that's smaller than negative root 2. Now, you might not know exactly what negative root 2 is, but you can test any value that's smaller than that. So like negative root 2 is about negative 1.4. So you could test negative 2, negative 3, negative 4. So why don't we just test like negative 3. So if you were to put a negative 3 in for this x, 4 times negative 3 would be a negative number. So I'm going to put a little negative sign to show that this factor up here would be negative. Now, if you put negative 3 in for this x in this factor right here, negative 3 squared is 9, 9 minus 2 is 7, that's a positive number. So I'm going to put a little plus in here. So we'd have one factor that would be negative and one factor that would be positive. 4x would turn out to be negative, x squared minus 2 would turn out to be positive. A negative times a positive, however, is a negative. So I'm going to write that f prime is negative. And then we're going to move right along, because we're not going to move right along yet. The fact that f prime is negative, remember what f prime is telling us about. It's telling us about the slope of the function. And so that means our function must have a graph that's going down like this. And then at negative root 2 here, we know that the function has a 0 slope. So I know my function's going to look like that. It's going to have a little leveling off spot. And now we're going to proceed across and test a value between negative root 2 and 0, like negative 1 would be a nice one. Now 4 times negative 1, that of course is going to be negative, and so I'll put a little negative in here for that factor. But now you'll notice that when you plug a negative 1 into this x, negative 1 squared is positive 1, 1 minus 2 is negative 1. So that means this factor now is going to be negative as well. So we have the product of two negatives, which will of course be positive. So that means our function must be coming up here. And so what we've just done is painted a picture of a graph that comes down, levels off, and then comes up. So that means that that spot right there at x equals negative root 2, is a min. It's a relative minimum, which means it's the lowest spot in its little neighborhood. Now let's continue across. We'd check a value of x in this interval between 0 and root 2, so we could check positive 1. Plugging positive 1 into this first factor, 4 times positive 1 would be a positive number. And plugging a positive 1 into x squared minus 2 would give you 1 squared, which is 1 minus 2, which is negative 1 again. So we get a positive times a negative, which is negative. And so what we now know is that the function must be going down here. And that means we have the function going up with a 0 slope and then coming down. So now it looks like we have a little maximum there. And so we're going to say x equals 0 is a max. I don't know why I wrote that there. Let's get rid of that. Okay. And we're going to do one more interval here, and we're going to check out and see what's happening with our function in this last interval. A number to the right of root 2, so we can use something like 3 again. Plug a 3 in here. 4 times 3 is positive 12, so it would be a positive. And then think about 3 squared. 3 going here, 3 squared would be 9. 9 minus 2 is 7, that's positive. And again, we'd have a positive there. And the product of two positives is positive. So our function must be coming up because we have a positive slope with a little 0 slope in there. So again, that guy looks like he must be a min. So x equals positive root 2 is a min. And now we have a really good idea of what that graph must look like. It must come down, then come up and have a max, and then come down and have a min, and then go back up again, which makes sense based on the fact that it's a 4th degree polynomial, and we know 4th degree polynomials have a tendency to look like this. So we're ready to tackle our second example here, and it's another one where we're going to try to find the critical numbers and then determine if they are relative maxes or mins. So again, we kind of have a picture up here, and it's a good rendering to see that when you find a relative min, sometimes called a local min, you can see like this one right here where the slope went from negative to positive. That's an important point, but when we discuss our next part of this lesson, when we're looking for absolute maxes and mins, we're going to find out that this point over here is going to be the winner of the absolute min rule because it's the lowest y value overall in this function because it's lower than this min. So that's something we're going to be tackling next. But for right now, let's get started with looking at this guy's derivative. So f prime of x is, let's see, we're going to bring that 3 down in front. That's going to make 3/2 of x squared. Then we're going to bring this 2 down in front and multiply it. And when we get 2 times 3/2 of x, those 2's are going to cancel, which is kind of a good thing. And then, of course, the derivative of 1 is 0. So cleaning this up, we have 3/2 of x squared minus 3x. And that's our derivative. So we want to find out when this guy's equal to 0. So I set it equal to 0. And I recognize that I have a common factor of 3x in both terms. So I'm going to take a look at taking 3x, let's take 3x out of there, and that's going to leave us with 1/2 of x minus 1. And again, when you are factoring, you want to make sure that you factored correctly. Distribute this back in there, you better get that term. Distribute it back in here, and you better get that term. And I think that checks out. So we have either 3x equals 0, which means x equals 0, or we have 1/2 of x minus 1 equals 0, which means 1/2 of x equals 1, which means x equals 2. So we just have two critical numbers, and we can set up our sign chart. So let's go do that with a 0 and a 2. Remember, we have to list these in ascending order. And I'm going to make a little note that we're looking at f prime here. That's going to be important later on because we're going to be doing some work in the future where we're looking at signs of the second derivative. So we might have two sign charts in one problem. So I want to make sure we keep our work clear. And again, we know that this function, its derivative, which has, the derivative's right here. And it's got two factors, this one and this one. And we know that the derivative equals 0 at both 0 and 2. So I'm going to make a note of that the derivative is 0 here and here. And I'm going to set up my parentheses like I did last time to kind of keep my work organized. So I can track the signs of each of these two factors. And we will test a value to the left of 0, which is like -1. Now when I put a -1 in here, in this first factor, that's going to be negative. And when I put a -1 in this factor, -1 times a half is -1/2, minus another one is -1.5, so that's going to be negative. We have two negatives multiplied together for a positive, which means our function has a positive slope. Moving on, between 0 and 2, we could test the value 1. 1 is a number between 0 and 2, and we'll test it on our two factors. 3 times 1 is a positive number, but 1/2 of 1, which is 1/2, minus 1 is still negative. So this guy is going to be negative, and a positive times a negative is negative, which means our function has a negative slope, so it's decreasing there. And then lastly, we move over to the far right, this interval to the right of 2, so you can test a number like 3. Again, plugging it into the first factor, 3 times 3 is positive. And oops, let's make a little plus there. And again, now when you plug in 3 in for this x, you're going to get a positive value because 3 halves, 1/2 times 3 is 3 halves, 1.5, which is 1.5, 1.5 minus 1 is positive, and we get a positive derivative there, which means our function goes back up. So it looks like we have a max here because the function goes up and then turns around and comes down, and then it looks like we have a min here where the function goes down and turns around and comes back up. Now this should make sense because we know that a cubic function, from what we studied in Algebra 2, tends to have a look that goes like this. So we could just make it clear that x equals 0 is a relative max, and x equals 2 is a relative min. And those are two good examples of relative mins and maxes for you to work on. Now we'll have an assignment where you're going to do a couple of these on your own. And then in the next lesson, we're going to move on to finding absolute maxes and absolute mins. That's where we're finding the absolute highest y value and the absolute lowest y value on a particular interval on a function. Till then, we'll see you next time.